Okay, as a reminder, objects undergoing simple harmonic motion have these position, velocity, and accelerations, these related sinusoids. Here we're assuming that the object starts at its maximum extent and then heads towards the origin, so they get a cosine. It's possible we'd start at the origin and start moving outward, in which case it'd have a sine, or even outward and the other way have a minus sign, and so on. So these could be other functions. If whatever happens to here, we'll change these as well, because this will always be shifted a quarter period this way, and this will be flipped of whatever the position one was. It will always, however, be that the maximum position is a, and therefore the maximum velocity is 2 pi f times a, and that the acceleration is the quantity 2 pi f all squared times a. And remember that these are the same as saying 2 pi over t times a, or 2 pi over t squared times a. So the rest of this video is going to be doing some of these problems, just giving some thought to what these things look like. Alright, figures show 4 identical oscillations at different points in their motion. Which object is moving fastest at the time shown? Well, we know that the maximum in the velocity curve is going to occur at a 0 of the position curve. That's a general feature of sines and cosines compared to each other. So wherever it's at its origin is where it's going to be going fastest, and we can see that that is here. Alright, classic children's toy consists of a wooden animal suspended from a spring. If you lift the toy up by 10 centimeters and let it go, it will gently bob up and down, completing 4 oscillations in 10 seconds. So what is the frequency of the toy? Frequency, remember, is repetitions per unit time. There are 4 cycles in 10 seconds, or 0.4 hertz. The same setup, and they say it bobs up and down the same amount. What is the maximum speed of the toy in centimeters per second? Here we use that V max is 2 pi f times a, so it's 2 pi times 0.4 hertz times 10 centimeters. So it would be 8 pi centimeter hertz, but that is 8 pi centimeters per second, because centimeter hertz is centimeters per second. Alright, same setup. If the toy is released at t equals 0, when will it first reach its maximum speed? Answer in seconds. Well, we know that it will reach its maximum speed when it first passes through the origin. And if this is 1 period, then we know the first time through the origin is 1 period over 4. So the time that we want is 1/4 period. And what is the period? Well, that means it's 1 over 4 times the frequency. So 1 over 4 times 0.4 hertz, which is something like 0.625 seconds. New setup. A mass spring system has a period of 8 seconds. Its equilibrium length occurs when the mass is at x equals 0. The mass is pulled to x equals 0.16 and released from rest at t equals 0. What is the amplitude of the resulting motion? Answer in meters. So there's a lot going on here, but we're going to use together that its equilibrium length is here, but then it's pulled to here and released, which means it's going to immediately move closer in. So if we sort of sketch this thing, we would have, we've pulled this some additional length, and then we're going to let go, and of course what's going to happen is it's going to move in. It's never going to get further out than this location. So the amplitude is this, 0.16 meters. Same setup. And we want to know when is it first at x equals 0. This is similar to the earlier one. We start here. This is our graph. We want this time. And this is 1/4 of the period. So the time we want is 1/4 of 8 seconds, or 2 seconds. Same setup, and we'd like to know when is it first passing through x equals 0.08 meters. In other words, halfway to its amplitude. This one, it turns out, you got to do some grungy work. We got to take that we've got to take this formula, and we're going to say at what t is x equal to 1/2 the amplitude. The actual grungy algebra of that is to just go through here and say, well, 1/2 equals that. Cosine of that equals cosine 2 pi t over t is 1/2. So we take the inverse cosine of both sides so as to liberate the time from the cosine argument. And we get 2 pi over the period times time is pi over 3. So we must end up at 1.33 seconds. What is its speed as it moves through that point? Again, we know that v is minus v max times the sine of the same factor, 2 pi little t over big T. We know that v max is 2 pi over big T times the amplitude. And so we can do the same kind of game. We say it's minus 2 pi over t times a times the sine of all that stuff. We know that we're at 1/6 period, so we can do a little cute thing here by saying we know that the sine of pi over 3, because we knew that that was what the argument was. And then we just do some grindy things, and we find out that the velocity is minus 0.11 meters per second, so the speed is 0.11 meters per second.